Hello everyone, my name is Ajay Mehdi. In this presentation, I am going to discuss about mechanical response of femur bone to bending load using finite element method. Abstract. Bending load is often encountered in femur bone, particularly in the case of lateral impact. Femur fracture is quite usual in pedestrians. It generally occurs because of bending of femur bone due to lateral impact. In order to prevent fractures in walkers and vehicle passengers from accidents, it is significant to study the bending behavior of femur bone. Femur bone is one of the most commonly fractured bones in the human body, as it is one of the longest and largest bones. In this work, mechanical response of femur bone to bending load is studied by the help of finite element stimulation. For a given critical load, deflection, von Mises stresses and bending stresses have been obtained. For a critical bending moment of 200 Newton per meter, the maximum von Mises stresses reaches up to 131.3 megapascal and the maximum deflection is found to be 1.8 centimeters. The von Mises stress must be less than the yield stress of the material, otherwise it could to fracture of the bone. In this figure shows the femur bone of a human body, and it is the longest and largest bone in the human body. Right. Next, introduction. The femur bone is the longest and largest bone found in the human body. It also known as the thigh bone. It connects to the pelvis at the proximal end to form the hip joint and to the tibia at the distal end to form the knee joint. Any lateral load on the knee joint acts as a bending moment on the femur bone. Thus, any kind of the accident of pedestrian or automobile passengers leads to the bending of femur bone. The stresses proceeded due to bending can lead to fracture of a bone as the maximum stress exceeds the failure criterion. The present study is in relation to bending of femur bone for a critical bending moment. This method was brought in orthopedical biomechanics in 1972 to measure stresses in human bone. As of today, this method is widely used in the area of orthopedic biomechanics. These examinations were meant to evaluate the relationship between the elements that affect the load and morphology of human tissues. FEM offers a cost-effective alternative in the biomechanical studies of stress analysis. Experimental bending tests. Generally, for bending analysis of bone, three types of bending tests are employed: the 3-point test, the 4-point test, and the cantilever test. In majority cases, 3-point test is applied. This test is performed by keeping the bone between two holders, with one holder at every end, and force is applied at the midpoint of the bone in the inverse direction. Holders are kept at right angles to the axis of the bone, with force acting vertically down at right angles to the axis of the bone and at the midpoint of the bone. The value of load is generally gradually increased till fracture of bone occurs. This test can be done on cortical bone specimens cut into approximate shapes, parallelepipeds. In 4-point bending test, a compressive force is applied to the bone with the help of a 2-arm device. The area of concern is kept between the two arms. Both the arms of the devices should contact the bone simultaneously in order to obtain exact results. This test is mostly employed when the most fragile location is not known, as the results are not influenced by placing the maximum bending moment at a specific site. In 4-point bending test, a compressive force is applied to the bone with the help of two armored devices. The area of concern is kept between the two arms. Both the arms of the device should contact the bone simultaneously in order to obtain exact results. This test is mostly employed when the most fragile location is not known, as the results are not influenced by placing the maximum bending moment at a specific site. While performing a cantilever bending test, one end of the bone is ground to a fixed structure, while the other bending force are applied to the free end. While performing a cantilever bending test, one end of the bone is ground to a fixed structure, while the bending force being applied to the free end. The bone is oriented to replicate various positions in these experiments. Bending tests were performed Helene, Bupide, Uric, Les Puceles, and others. The results are tabulated as under. Bending stimulation by finite element model. Finite element stimulation prediction depends entirely upon the geometry considered, the loading conditions and boundary conditions. For this reason, accurate FE model of femur bone with accurate geometry are very important. The geometrical information of a patient specific femur bone was obtained from CT data by Nasley. The CAD model is not perfect replica of the human bone, as the bone is of complex shape with complex surfaces and boundaries. However, the software models the geometry by using splines, which is good enough for performing a FE stimulation. A FE model based on this geometrical information was constructed using meshing software GMSH with 2958 tetrahedral elements with 8-9 nodes. Material. Human bone is highly heterogeneous and non-linear in nature. To perform the FE analysis, the bone was presumed to have isentropic linear elastic material properties. The density was chosen to be 866 kg per meter cube based on the samples average of the largest elderly group, while the Poisson's ratio was chosen to be 0.4. The Young's modulus was calculated from the density using reported correlation and was found to be 7.585 gigapascal. Equation: von Mises stress. When the second deviatrix stress invariant approaches a threshold value, von Mises yield criterion recommends that the material has started yielding. Before yielding material responds to be elastic. Von Mises yield criterion is mathematically expressed as J2 is equal to K square, where K is the yield stress of the material in pure shear. As the yielding starts, the shear yield stress magnitude in pure shear is under root of 3 times smaller than the tensile yield stress in the case of simple tension. Thus, K is equal to sigma y, where sigma is the yield strength of a material. Combining the above equation by setting von Mises stress as yield stress, the von Mises yield criterion is given by. Result: in our finite element stimulation, we performed a cantilever bending test on a femur bone model. As mentioned earlier, in cantilever bending test, one end of the bone is kept fixed and the load is applied on unsupported end. The boundary conditions were applied on the femur model, with researchers have shown that the critical value of bending moment for fracture of bone is 200 Newton meter. Based on the critical bending moment, the magnitude of bending load applied is 500 Newton. The results obtained are discussed as follows. Bending stress along the axis of femur bone. In this figure 3 shows the bending stresses induced in the femur bone along its axis. The reading is shown on the left hand side of the figure, shows the value of stress corresponding to the color in the bone. The result, the unit of these stresses is Pascal. The maximum bending stress is femur reaches up to 64.9 megapascal. P. Von Mises stress. From the finite element stimulation, von Mises stress was obtained as shown in figure 4. We can clearly see that von Mises stress reaches up to 131.3 megapascal in the distal end from where the load is applied. As in a cantilever, the maximum stresses are the root of cantilever. Similarly, in this stimulation, the maximum stresses are near the fixed end region. On the other side branches, the loading has not been transmitted and therefore the stresses are minimal. Displacement magnitude.